Okay, so in this mini lecture, I will introduce to you the Duhamel principle for the non-homogeneous wave equation in one dimension. Let me write out the equation. The equation is simply that we would put a source term on the right-hand side. So I have UTT minus UXX equals to f of xt, which is a source term in R plus 0 infinity. And let's say I'm given simple initial data that ux0 equals to 0 uh, on R. So we start with 0 um, position and also 0 velocity. So ut of x0 equals to 0 on R. Okay. So as noted, this is a source term, right? And then so we have f xt is a given source term. And let's say f is continuous, which is continuous, right? Continuous. So we want to use the Duhamel principle to solve this non-homogeneous wave equation, which is familiar to you guys because we have done the Duhamel principle for the non-homogeneous uh, heat equation, but it's a little bit different here because we have two derivative in time. So you need to be a bit careful to see where do we put the source term as the initial data, right? So let me say it like that. Okay, so the Duhamel principle. So, so we have seen this, we saw this for the heat equation. So here we just need to be careful to see where to interpret f as an initial data, right? I put it in quotation because we just need to interpret it. All right. So to make it clearer, let me give an example that we consider even just the OD case. To understand better the intuition, and then we come back to the wave equation, right? So example, just ODE. Okay, so second equation I'm considering here, ODE here, by that I mean that there is no spatial dependence, meaning that I assume that f of xt is just f of t, so no spatial dependence. And because of no spatial dependence, I'm gonna look for our solution u, which is also not depending on x, right? Because there's no spatial come into play. So I'm gonna just look for uxt is simply some, let's say, v of t. Okay, then uh, v gonna satisfy the equation. You can look at one there. You copy it down, right? You write out the equation for v because there's no spatial dependent. I simply have v double prime of t equals to f of t for t greater than 0. It's a very simple ODE, right? And then I have v of 0 equal to 0 and v prime of 0 equal to 0. That's our ODE, and to solve this, we just need to integrate it twice to get the solution, right? So okay, so now let's write it out like that. Um, yeah, so then just by the fundamental calculus, right? The fundamental theorem, calculus, we have Vt, which is equal to V0 plus integral from 0 to t V prime of s ds, right? And we are given that V0 equal to 0. So this is 0 plus integral from 0 to t V prime of s ds. Okay. And now I'm also using the fundamental theorem for of calculus again for V prime. So this equals integral from 0 to t, and V prime of s is equal to V prime of 0 plus integral from 0 to s um, V double prime of a dA, okay, and everything ds. And again, I'm using the fact that V prime of 0 is also given to be 0. So this just simply equals to integral from 0 to t, 0 to s. V double prime of a is given to be f of a, right? So this is f of a dI ds. And that's the formula. That's it, right? But we can interpret, or we can think about this a little bit more, right? I mean, because this is a double integral, but we know the domain of integration quite clearly. So let me draw the picture of the domain of integration maybe up here. So this is I'm drawing the domain of integration. I label this is, let's say this is S and this is A, because we do dIds, right? So we know that S is running from 0 to t. Says S is running from 0 to t, and h for each of the s, a is running from 0 to s, right? So for each of the given s here, a is going from 0 to s, so a is going from here to here. Okay, this is s. So a is going from 0 to s. Yeah. So you can see that the domain of integration is exactly this triangle, this right triangle that have isosceles right triangle. Okay, this is our domain of integration. Okay, let's call that D to be consistent with our lecture notes. Okay, so let me conclude that I have Vt is equals to the double integral in D of Fi di ds. That's a given formula, right? And this also allows us to actually, by Fubini, we can do integration in the other way, right? Instead of do di ds, we can do ds di. So if we do ds di, so let's look at that. So if I do ds di, then meaning what? I see that I is also running from 0 to s here, right? Sorry, to t here. I is running from 0 to t, and for each of the I see that you can see in the I'm sort of working on the figure here. You can see that s is going from a to t. Okay, so by Fubini, let me write down. So then by Fubini's theorem, we also have Vt equals to integral. Again, I'm doing integral in a later and in s first. So a is from 0 to t, and s is running from a to t. Okay, of fi ds and then di, right? And for the first integral inside here, fa is a constant with respect to ds, right? So the integral is simply equals to the length of the interval, which is t minus a times fi, right? And then di. Okay, so I have a new formula for v, which is just this integral. Okay, so that's a normal way to look at problem two. You just integrate it twice, right? And there's the other way to look at problem two, like what we have been talking about Duhamel principle. The other way to look at it is that we're gonna actually interpret f as a source as opposed to a source term as an initial condition, right? And in this case, you can see that it should act as the initial condition for V prime, right? Because V double prime is F, then V prime is a, is the antiderivative of F. So clearly that a natural way to look into the Duhamel formula. So maybe so Duhamel principle here is that naturally what I'm gonna look at is that I'm gonna look as for h s greater than 0, I'm gonna input in f as a initial data for v prime, right? Because again, v double prime equals to f, so v prime should take into account f for the Duhamel principle. So the equation that I'm looking at for 3, let me call, is that I denote by vs double prime is equals to 0, right? Okay, so Vs double prime of t should equals to 0 for any t, okay? For t great, for let's say t in R, that's okay. And then as a given time s, I have Vs of s equal to 0, but I have Vs prime as s should equals to f of s, right? So I'm interpreting f of s now as a um, as initial data for v s prime at time s. Okay. So again, that's the Duhamel principle. Instead of interpreting f as the source term, you think about that as each of the time that you put the source in, you just single it out and think of it as a new initial data and see how it goes. The key point here is that the initial data should be put in V prime, not V. Okay. So let's compute and double check that is equals to the above formula that we just see. Okay. Um, so here, well, I mean, Vs double prime is 0. So that means that in this case, Vs prime t is constant, right? Is constant. So that means that I should have Vs prime of t should equals to Vs prime of s, which is f of s for OT. For OT. Okay. That's what I should have. So if I integrate this, I should have then that I should have Vst should equals to Vs ss plus integral from s to t Vs double prime, oh, no, prime, not double prime, of RdR, and this is a constant. This is f of s. So if I integrate, I see, and this is 0. So if I integrate, I see that this is nothing but fs times t minus s, right? Just the interval of integration. And now you can see that when we single out each of the initial, each of the source term as initial condition, we run it, and then eventually we have to sum all the contribution together to get back the v, right? And you can see that this means that then I should have v of t is nothing but the summation of all contribution, which is integral from 0 to t vs uh, of t ds, right? Because that's the contribution for each of the s, and I sum it up from time 0 to t. So this is exactly integral from 0 to t. You see, this is fs or fa, right? Okay, yeah, okay, doesn't matter. Let me write t minus s fs ds, or, if you want to be consistent with the above, which is integral from 0 to t minus a fi di. Okay, so it's exactly consistent with the formula above. Let me highlight them. So I'm highlighting the above here, and that is by direct computations. And now I'm highlighting the below one. This is computed through the Duhamel principle. Okay, so because of that, now I know exactly what to do for a more complicated problem, which is the heat equation, right? So it's now become quite simple. That now I'm ready for the heat equation. So sorry, for the wave equation. Let me recall that the wave equation one here, I have utt minus uxx equals to f, and f is a source term. Now I'm gonna interpret f as the initial data for ut, right? At each of the time, I'm gonna solve that problem, and then I'm gonna sum everything back to get back the solution to this general uh, wave equation. Okay, so now let's get ready. So we are now doing Duhamel principle for wave PDE in 1D. Okay, maybe let me write that one again in case you forget it. I have utt minus uxx equals to fxt. Ux0 equals to ut of x0 equals to 0. Okay, so the corresponding problem that I'm considering for Duhamel principle is that for h s greater than 0, we can let us solve the equation. Let me call it 4, that I have us of tt minus us of x equal to 0. So that's just a homogeneous wave equation in R times time from S to infinity. Okay, I put that US at XS is 0. Okay, um, so I'm not changing the position, but I'm changing the velocity. The velocity UST of XS is given to be exactly F of XS on R. So the velocity here is now being put as f, which is sort of considered to be the initial data for this equation. And for this equation, we have already solved it. We have the formula for this, right? So the formula for us is known, which is us of xt is given to be just the integral of the velocity, right? So 1/2 of integral from x minus t minus s to x plus t minus s of f y s dy for x in R and t greater equals to s. Okay, so that is the formula we have. So now let me state the theorem for this mini lecture, and we're going to prove it quickly and we are done. Is that we're going to have that the solution to 1 is uxt is exactly summing up all the contributions from the source term being considered as initial data. So we're going to sum everything back. So uxt is going to be integral from 0 to t us of xt ds. So we are summing up all the contribution, right? And if you write out the formula, we have an explicit formula: 1/2 integral from 0 to t integral from x minus t minus s to x plus t minus s f y s dy ds. Okay, you have this explicit formula. Okay. The proof is quite straightforward. The key is to understand why we put f on ut of s. Okay, proof. Let me change the color. Okay. Well, yeah, we just need to use the first formula, right? So let me write out uxt equals to integral from 0 to t us of xt ds. So I can differentiate in x because the integral is in t. There's no x dependence here. So I see that uxx of xt is nothing but okay, let me write um let me write del square over del x square of this integral us of xt ds, and I can put the derivative of x inside, so this is equal to 0 to t, us of xx xt ds. Okay. Um, and because us solves the wave equation, so this is equal to integral from 0 to t us of tt x s ds. So that is known. Now, computing the derivative with respect to t is more complicated because t appears both inside and also on the integral. So we need to compute with care, right? Now we compute utt of xt, right? Let's do it step by step. Let's compute ut of xt first. This is del over del t of this integral from 0 to t, us of xt ds. Again, t appears inside, right? So I can put the derivative inside. I would have ust of xt ds, and it's appear on the integral, right? So if I differentiate on the integral, I would have, by the fundamental theorem of calculus, I would have the us of xt evaluated as s equals to t, which is ut of xt. Okay. Now, if you look back at the formula, right, you have us of xs equal to 0. So that means that ut of xt, this is given to be 0. So that's 0. Now I have then ut of xt is still just integral from 0 to t ust of xt ds. Okay, let's compute it once more. Utt of xt is del over del t of this integral. And we use the same rule, right? So either we put the derivative inside, I would have us tt of xt ds, or if I differentiate on the integral, I would have that is ust of xt evaluated at s equals to t, which is ut t of xt. And if you look back at the formula, we are given that ust of xs is fxs, right? So this is given to us as exactly the source term interpreted as the initial velocity. So this is exactly f of xt. Okay. Now if you compare the two formulas, uxx equals to integral from 0 to t us dt xs ds, and utt equals to this integral, exactly that. And we have the additional term, which is f of xt, represents for the source term, right? So combine the two together, um, combining the calculation together, we get exactly that utt minus uxx equals to f of xt. Okay, so we are done, right? So great. So we have the formula that exactly that you can see that the formula is that, let me highlight it. Uh, is that I have uxt here equals to exactly the contributions of O of us of xt, where we sum O over s from 0 to t. And of course, if you write down explicitly, uh, you're gonna have that uxt equals to this formula. So let me conclude by just drawing what does it mean in terms of the figure, what this formula, right? So let me make a remark to conclude. So a remark is that what's the formula? I have uxt equals to 1/2 integral from 0 to t, integral from x minus t minus s to x plus t minus s, f ys dy ds. Okay, so if you draw out the region, so let's say this is x, this is t. Let's say that I start with this point xt here, This is x, this is t. Then you start when s equal to 0, you start from x minus t to x plus t. And then for any other point, if you start at s here, this is s, then you start from x minus t minus s to x plus t minus s. So as a result, you are integrating exactly within this triangle. Okay. So you can name this triangle, I think in the notes, and name it dxt. Then you have exactly a beautiful formula that you have uxt is 1/2 of the integral in this triangle of dxt f of ys dy ds. Okay, so we are done with using the Duhamel formula principle for the um, non-homogeneous wave equation. So let me say that you start with the non-homogeneous wave equation, and you're gonna try to interpret the source term as the initial data of the velocity of ut, right? So that was demonstrated through the ODE, but basically you would put ust of xs equals to fxs, you solve for us, and then you sum it up, you integrate us of xt with respect to ds for s from 0 to t to get the result. Okay, so let me stop.